for what we have in number 5, okay, we have xy plus y prime is equal to 122x. And again, you can use Leibniz's notation. And this is one that you can also solve, okay, separating the variables and factoring out x. Or again, you can use the integrating factor. And here, just doing the commutative property of addition switch around, putting the dy over dx at the front. Okay, we have dy over dx plus xy is equal to 122x. Now for the integrating factor, we say we have e to the integral. Okay, we have the coefficient of the linear y term to be at x. So you're looking at e to the integral of x dx is equal to e to the x squared over 2. And if we multiply these terms out by the integrating factor, okay, we have e to the x squared over 2 dy over dx plus x times e to the x squared over 2 times y is equal to 122x times e to the x squared over 2. And for what we have on the left hand side, again, for what results is going to be the product rule expansion of taking the derivative in x of the integrating factor e to the x squared over 2 times y. Again, we have this equal to 122x times e to the x squared over 2, and freeing up the terms in the brackets. Okay, we have e to the x squared over 2y is going to be equal to the integral of 122x times e to the x squared over 2 dx. And for what is going to arise, okay, if you're to think along the lines of substitution, if you're to take substitution for x squared over 2, the derivative is going to go to x. And for what would result as the antiderivative would be, in this particular case, 122 times e to the x squared over 2, and then we have followed by the constant. And so for what we would have in this particular case is that as we look at isolating the variable y and solving, okay, so we can divide both sides by e to the x squared over 2, and in this particular case we had that y is equal to 122, and we say we have plus c, and we have times e to the negative x squared over 2. Okay, so you have 122 plus c times e to the negative x squared over 2, and that is our general solution for problem number 5. Now, for what we have in the case of problem number 6, okay, we have for the setup here, okay, we have a graph. Again, this time we're going from 0, 1/2 to 9, 6. Okay, and we're looking at finding the exponential function y is equal to c times e to the kt that passes through the two given points. Okay, so we have in this setup, okay, we have in number 6, okay, we have of the form y is equal to c times e to the kt, and we have for the initial point, okay, we have that at time 0 y is equal to 1/2, and if we were to carry over, we would have that 1/2 is equal to c times e to the 0. E to the 0 is going to go to 1, so automatically c is equal to 1/2, so we had that y is equal to 1/2 times e to the kt. And for what we have in the follow through, okay, to satisfy our other point, we have that at t is equal to 9, y is equal to 6. And as we carry over what we have here, substituting, okay, y is at 6 whenever t is at 9, so we have that 6 is equal to 1/2 times e to the k times 9, or 9 times k. And multiplying both ends by 2, we have that 12 is equal to e to the 9k. And looking at solving for k, we have taken the natural logarithm of both sides. Okay, it's going to follow that for k itself. Okay, so we have 9k. It's going to be equal to the natural logarithm of 12. And so k is going to be equal to 1/9 of the natural logarithm of 12. And you can approximate this to about 0.276. Okay, so we have for our general expression, we have that y is equal to 1/2 times e to the kt. And now that we have the approximate value for k itself, we can say that for the outcome in approximating, we had that y is about equal to 1/2 times e to the 0.276 t. Now, and what we have in item number 7, okay, we are now looking at a situation where we are looking at compounding interest. And so for what we have in this particular setup, okay, we have for compound interest, it says to find the principal P that must be invested at rate R so that $500,000 after the investment is compounded monthly will be available for retirement in T number of years. Okay, so we have, in this particular case, we have for number 7. Okay, we were looking at monthly compounding, and so we are looking at utilizing compound interest formula, so we can say that we have A is equal to P times the quantity of 1 plus R over N to the N times T power. Okay, and we're looking at $500,000 for the future value. And we are finding out, okay, what the value of P is going to become. And for the rate of interest, you have it 6%, so we record R as 0.06. Monthly compounding, N is going to be at 12. Then we have to the 12 times 30. So we have 500,000 is equal to P, and the sum of 1 and the quotient of 0.06 over 12 is going to be 1.005. 12 times 30 is going to be 360. And so for what we have in the case of P itself, if we isolate, we say that P is equal to 500,000 all over 1.005 to the 360. And so for what we have as the approximate value of P, we're looking at 83,020.96. Of course, you can round up or round down. And so carrying out, say, in full effect, okay, without rounding up or down from the very start, we say that approximating, okay, we had that the principal is going to be about $83,020.96.